Hello, this is Drytree. It's been a while. While preparing for this podcast, I realized there are so many things I couldn't say in my YouTube videos, articles, or lectures. So, I'm doing this podcast to talk more comfortably about what I want to say. I have over 20 to 30 topics ready, but I haven't had time to record because I've been busy. Just a moment ago, I was at the John and Gu Economic Research Institute channel. It's often a symbol of memes and mockery on YouTube, but it's very comfortable to talk there, and the location in Gangnam is great. I chatted there for about 2 hours. The main themes were AI, energy, quantum, and space. Promising technologies or next AI-related content. On such public channels, it's hard to discuss technical specifications in detail. So, through this podcast, I want to talk more about those parts. AI consumes a lot of electricity, increasing the need for energy. On the ground, this demand can't be met easily. Building a power plant takes 10 years, and laying the transmission grid takes about 7 years due to regulations and local opposition. There are discussions about operating data centers in the sea. Microsoft previously did this in Scottish waters by submerging capsules. China is also doing this in Shanghai. Recently, Peter Thiel invested $140 million in a startup called Fantera, which builds floating platforms on the sea. They aim to use wave power for AI inference servers and satellite communication. However, in December last year, Elon Musk touched upon the theme of space data centers. Shortly after, in early February, he merged xAI and SpaceX. Around mid-June, likely near Elon's birthday on June 17th, he plans to do something significant. SpaceX originally wanted to stay private because Tesla's listing was so difficult. But Starship needs money, and Elon needs to challenge Sam Altman. He is chasing AI through the Grok service via xAI. OpenAI is quite solid despite current crises. Anthropic's Claude is also pushing forward in business. Compared to ChatGPT, Claude, and Google's Gemini, Grok's presence is relatively small. But he built the Colossus data center in just 122 days using 100,000 NVIDIA GPUs, and plans to add 300,000 more. This requires massive spending on electricity. Elon is a master of vision. He connects AI, space, and energy into a single concept, space data centers. Through Starship, which aims for a payload of 100 to 125 tons, compared to Falcon 9's 25 to 40 tons, he can launch over 3,000 satellites like Starlink, each loaded with NVIDIA chips. These would essentially be 3,000 orbiting data centers, each around the 1 megawatt class. Solar power in space is 36% more efficient than on Earth because there's no atmospheric scattering, clouds, or dust. You don't need to buy land. You just use space. With 10,000 Starlink satellites, they already have the know-how for swarm operation. The hurdle is heat dissipation. Since there's no convection, you need massive radiators, the size of 4 or 5 tennis courts for a 1 megawatt center. There are also issues with space radiation and durability. Making chips survive in space makes them 3 to 5 times more expensive. The most critical factor is the launch cost. Currently, Falcon 9 costs $2,000 to $3,000 per kilogram. This needs to drop to $200 to $300 to be economically viable compared to ground-based power costs. The storytelling is great, but realistically, this won't happen until 2035 at the earliest. The upcoming Starship launches are mainly heat shield experiments for the V3 airframe. The Artemis project also relies on Starship for lunar landings, but progress is slow and FAA approvals are difficult. To be economically viable, they need to launch over 150 times a year. They are building more launch sites in Florida, Starbase, and Vandenberg to reach a frequency of 200 launches a year. During this gap, IPOs will provide necessary capital. They will also receive chips through Terral, likely referring to Tesla's internal chip efforts, for both space data centers and Tesla's FSD and Optimus. Elon was criticized for buying X, Twitter, for $44 billion, but now he has real-time data for Grok. Combined with Tesla's FSD miles and Optimus humanoid data, plus the Dojo supercomputer and Starlink, the storytelling for a physical AI infrastructure is very strong. However, the investment from Amazon, Microsoft, Google, and Meta is in the hundreds of trillions of won. If you don't pour money in, you can't keep up. Regarding quantum and AI, quantum is in a very early stage, mostly just playing around in labs with 10 or 50 qubits. Commercialization requires thousands of qubits. Qubits are very sensitive to temperature, heat, and dust, which causes errors. However, as AI develops, Google DeepMind's AlphaFold has already solved protein folding, winning a Nobel Prize. AI can use quantum technology for specific algorithms in drug discovery and battery material simulation. It's also great for military-grade cryptography and communication. As AI GPU power density increases, data centers are moving from air cooling to liquid cooling. About 30 to 50% of new builds use liquid cooling. NVIDIA's Blackwell, NVL72, aims for 200 kilowatts power density, and uses direct-to-chip liquid cooling. This is spreading rapidly among hyperscalers. New materials like silicon carbide, SiC, and gallium nitride, GaN, are gaining interest for power semiconductors because they support higher voltages and efficiency. The industry is looking at an 800 VDC architecture as the next standard. Data transfer bottlenecks are also an issue. While H100 uses about 700 W, B200/B300 will exceed 1,000 W. This requires 2.5D or 3D chiplet packaging. Emerging technologies like silicon photonics, using light instead of electricity, and co-packaged optics, CPO, are starting to spread to maximize data speeds. We are moving from PUE power usage effectiveness to PCE power compute effectiveness, measuring how much AI performance is produced per unit of power. In March 2026, Google and Caltech-based startup Oratoric published papers on using quantum technology to break codes with fewer resources. AI is now being used to search for quantum algorithms and correct errors. AI develops quantum, and quantum solves AI's computational bottlenecks. It's a symbiotic relationship. The QAOA, quantum approximate optimization algorithm, is used for finding optimal combinations in drugs or materials. IBM and Oak Ridge National Laboratory are using this to solve power grid allocation problems. Calculating power supply from various plants to substations in real time is incredibly complex, but quantum can do these calculations simultaneously. In Germany, the DLR, Aerospace Center, is using quantum for simulations in aerospace and energy, calculating stable atomic structures for better energy density and hydrogen production catalysts. Space data centers still face huge technical hurdles, likely to be addressed between 2035 and 2040. Heat must be dissipated via radiation infrared, because there is no air for convection. According to the Stefan-Boltzmann law, the heat radiated is proportional to the fourth power of temperature. Space is cold, but if the temperature is low, the heat radiated is small even with large radiators. Carrying these massive radiators into space is the real economic problem. This is why Starship's success is the core of SpaceX's story. They need to catch 1,000 to 3,000 errors through testing. Laser communication is being explored to replace traditional RF radio frequency. If you calculate in space, you need to get the data back to Earth efficiently. China has been experimenting with quantum satellite communication, MOSI, since 2016. In quantum communication, if a third party, C, tries to eavesdrop on A and B, the observation causes the qubit to collapse, letting the parties know someone is listening. Comparing Rocket Lab and SpaceX. SpaceX is valued at $175 to $200 billion, while Rocket Lab is around $4 billion. One-third of Rocket Lab's revenue comes from satellite parts. Their Electron rocket only carries 300 kilograms. Their upcoming Neutron rocket, targeting 13 to 15 tons, could compete if it's 15% cheaper than Falcon, but SpaceX dominates. If Starship carries 125 tons at a time, it's a different game. Tesla is also aiming for chip design and packaging via Dojo. Space data centers will use these AI chips. This connects to national security as well. Space is full of strategic assets like ICBMs and spy satellites. International laws in space are vague. Currently, the strongest player wins. Quantum computers won't replace general CPUs/GPUs, but will specialize in optimization and cryptography. Elon says space data centers in 3 years, but that's Elon time. It will likely take longer. Initial uses will be for defense, monitoring, and some edge computing. Once launch costs hit $300 per kilogram, a decentralized orbital AI infrastructure becomes realistic. No energy, no computing. No computing, no AI. No AI, no national power. Korea must catch up. We are technically in the top 3 along with the US and China, but the gap with the top 2 is huge. There isn't a lot of real money being made in AI yet, mostly just subscriptions and potential. Korea's aerospace efforts, CASA, need more independence and bold imagination. Instead of just copying SpaceX's reusable rockets, we should focus on niche materials, application technologies, or satellite services like direct-to-smartphone communication. I've spoken a lot today with a passionate heart. I have many more topics like OpenAI's crisis and Anthropic's rise. Google's Gemini isn't in great form lately. I'm writing a book on AI strategy war out late June, and another on new space. A book on 2027 deep tech trends will come out between September and November. This will be my 5th, 6th, and 7th books. Please show your interest. My goal for this podcast is to talk comfortably like chatting with friends. I'll try to do content in both Korean and English depending on the situation. Thank you.